After studying this module, you shall be able to know about magnetic properties of the transition metal ions, know about the magnetic properties of coordination complexes on the basis of crystal field theory, learn that the magnetic moment of the most of the transition metal ions are very close to spin only magnetic moment mu s. Identify the transition metal ions having magnetic moment higher than spin only magnetic moment mu s. Evaluate the reason for having the higher magnetic moment. Stop.
Magnetic properties of transition metal ions. The first transition group elements possess an incomplete inner 3D shell, but for these elements, the incomplete shell is not effectively shielded from external influence. These 3D orbitals are greatly affected by the ligands such that the rotations of electrons about the nucleus, which are essential for generating the orbital magnetic moment, get significantly restricted. It explains L becomes 0. This leads to great difficulty in estimating the degree of quenching of the orbital contribution to the magnetic moment. But in some cases, the results are actually easier to interpret than are those for the rare earths. The ions of the first transition series, starting from scandium 3 plus ion and ending with zinc 2 plus ion, have progressively 0 to 10 electrons in 3D shell. The first and the last member are diamagnetic, but all the other with intermediate number of electrons are paramagnetic. It might be supposed that these ions would be alternately paramagnetic and diamagnetic, depending on whether they had an odd or an even number of electrons. But as for the rare earths are concerned, the ions are all paramagnetic because the electrons in the incomplete shell tend not to pair off until these are forced to do so. For instance, in the 3D shell, there are 5 orbitals which can accommodate 10 electrons. If 6 electrons are present, they will take one paired and four unpaired place instead of three pairs. The four unpaired electrons will contribute to the paramagnetism. It is therefore an easy matter to complete the number of unpaired electron spins in any given ion. The difficulty that arises is in connection with the orbital contribution. The orbital movements of these ions are not free to move as they are for the rare earths, and yet, on the other hand, they may not be entirely quenched. But the best agreement with the experiment is obtained by completely neglecting the orbital motion. For all the transition metal ions, the magnetic moments are calculated by using following equations. First equation is mu j is equals to under root j plus 1 g beta, and the second is mu l plus s is equals to under root 4s s plus 1 plus l into l plus 1 beta. For spin only magnetic moment, capital L is equals to 0. So J becomes is equals to S, hence G is equals to 2. Therefore, the equation reduced to mu s is equals to under root 4s into s plus 1 beta, or on simplifying equation, mu s is equals to under root n plus 2 beta, where n is the number of unpaired electrons. Now let us calculate mu j, mu l plus s and mu s for one transition metal ion using equation 1, 2 and 3. For example, chromium 3 plus has D3 configuration, so that total spin quantum number S is equals to half plus half is equals to 3 by 2. Spin multiplicity 2s plus 1 is equals to 4, and the total angular momentum number capital L is equals to 2 into 1 plus 1 into 1 plus 0 into 1 is equals to 3. Now J can have values from L plus S to L minus S. It explains it can have 9 by 2 to 3 by 2. According to Hund's rule, J is equals to 3 by 2 is chosen for the calculation of G. Now G is equals to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2j into j plus 1. On putting the values of S, L and j, G becomes equal to zero point 0.4. Now the calculation of mu j. Mu j is equals to under root j into j plus 1 G Bohr magneton. Now putting the value of G and J, mu J comes out to be 0.77 Bohr magnetons. Similarly, we can calculate mu L plus S by putting the values of capital L and S into the formula mu L plus S is equals to under root 4S into S plus 1 plus L into L plus 1 Bohr magneton. The value comes out to be 5.2 Bohr magneton, and mu S can be calculated by using formula under root n into n plus 2 Bohr magneton, which comes out to be 3.87 Bohr magneton. Observed mu effective for the chromium 3 plus ion is 3.68 to 3.86 Bohr magneton, very close to spin only magnetic moment mu s. Similarly, mu j, mu L plus s and mu s can be calculated for the other transition metal ions. The calculated and experimental magnetic moments are shown here on the screen in the table. Now from the table, we observed that the magnetic moments obtained by using mu j equation are different from those worked out by applying mu s equation. Further, the magnetic moments obtained by using mu L plus S equation are different from those worked out by using mu S equation. We also know that if L is equals to 0, then mu L plus S equation reduces to mu S equation. Thus, magnetic moments of most of the first transition series metal ions are given by the mu S equation. However, the experimental magnetic moments of cobalt 2 plus and nickel 2 plus are found to be very higher than the calculated from the mu S equation. Magnetic properties of coordination complexes, crystal field theory. The magnetic behavior of coordination complexes can be easily explained using crystal field theory. In general, the ligands having very high splitting energy leads to the formation of low spin complexes. Since the gap between T2G and EG level is much higher, however, for low field ligands, splitting are less, thus they lead to the formation of high spin complexes. Now consider the complex. First, hexacyano iron 2 complex and hexaaqua iron 2 plus complex. In both the cases, Fe is in the plus 2 oxidation state and has octahedral geometry, but the complex with cyanide as ligand form a low spin diamagnetic complex, whereas the complex with H2O as the ligand form high spin complex. This can be explained on the basis of different ligand coordination taking place with the same metal ion, that is cyanide and water in this particular case. Cyanide is a strong field ligand that leads to high amount of crystal field splitting and thus forms low spin complex, whereas water is a weak field ligand which give rise to lower splitting and thus forms high spin paramagnetic complexes. This difference is explained with the help of the following figure. We can see that the hexacyano complex has large splitting as compared to hexaaqua complex. There is no unpaired electron in case of hexacyano complex as compared to hexaaqua where we have 4 unpaired electrons. So the hexacyano complex is diamagnetic, whereas hexaaqua complex is paramagnetic. Hence, the ligands lying at the end of the spectrochemical series are high field strong ligands which form low spin complexes. Examples include ethylene diamine, cyanide, and carbonyl, etc. As we have already discussed that the magnetic moment mu for the complexes of 3D metal ions can be deduced from spin only formula. This formula works reasonably well with the metal ion of the first series. In case of the metals of second and the third transition series, this equation is not applicable. For 4D and 5D metal ion, the angular orbital movement along with spin motion makes a large contribution. Since the complex hexacyano iron 2 is diamagnetic in nature, thus its magnetic moment is zero. But for the hexaaqua complex, it can be calculated as follows. For the hexaaqua complex, n is equals to 4. So mu s is equals to under root 4 into 4 plus 2. That becomes equals to 4.9 Bohr magnetons. Observed mu effective for the high spin complexes of iron 2 plus is 5.10 to 5.70 Bohr magnetons, which is very close to spin only magnetic moment mu s. Now the calculated and experimental magnetic moments for complexes of 3D transition metal ions are shown on the table on the screen. spin-orbit coupling. As already pointed out, that some of the first transition series metal complexes give magnetic moment much higher than calculated from the mu s equation. So every metal ion except for D1, D2, low spin D5 and high spin D6 and D7 follow spin only formula. The valence bond theory does not offer any explanation for this higher magnetic moment, but the crystal field theory does. As we know that classical model of orbital magnetic moment assumes that electron have to go around the nucleus so that Ampere's theorem is applicable. In most of the transition metal complexes, the motion of electrons is very much restricted so that effectively orbital magnetic moment is quenched. The unpaired electrons in first transition series metal ions are located in 3D orbitals. A transition metal ion has 5 degenerate 3D orbitals. In order for these electrons to the orbital magnetic moment, the electrons should go around the nucleus via these orbitals. In such a case, spin-orbit coupling takes place and contributes to the overall moment. It explains mu effective is greater than mu s. Spin-orbit coupling is the interaction of an electron's orbital angular momentum and its spin angular momentum, leading to a magnetic moment. For spin orbit coupling to occur, the following three conditions must be satisfied. First is there must be a half-filled or empty orbital similar in energy to the orbital holding the unpaired electron or electrons. Second, there must be a half-filled or empty orbital similar in shape and symmetry. It explains they should be transformable into one another by rotation about same axis. And the third condition is the nearby symmetry related orbital must not contain an electron with the same spin as the first one. Now the electron in this orbital can make use of this nearby orbital vacancy to circulate around the center of the complex and generate orbital momentum. It explains mu L. This leads to additional magnetic moment, as we know that spin orbit coupling means that capital S and capital L do not operate independently and J states need to be defined. But spin orbit coupling is usually small. For lighter transition metals, we can treat S and L independently. This is not true for heavy metals and their magnetism is much more complicated to predict. Orbital contribution to the magnetic moment in transition metal ions. Orbital contribution from e.g. orbital set. From orbital angular momentum to contribute and hence for the paramagnetism to differ significantly from the spin only value. The orbital in which electron resides must be able to transform the orbital it occupies into an equivalent and degenerate orbital by a simple rotation. In a free ion, the 5d orbitals are degenerate and some orbitals can be transformed into one other by rotation. The figure on screen illustrates that a 90-degree or 45-degree rotation about z-axis transform dxz to dyz and dxy to dyz or dxy to dxz and dxy to dx square y square orbitals respectively in all octahedral complex. Due to crystal field splitting, the 5d orbitals split into two set of orbitals of different energy that are T2g and Eg. The energy barrier between these two sets restricts the orbital magnetic moment of the electrons. The degeneracy between the dxy and dx square y square orbitals is also removed. The transformation of dxy to dx square y square is now restricted. In an octahedral field, dx square y square and dz square orbitals are degenerate, but the shapes of these orbitals are such that one is not transformable into the other by rotation. Thus, due to the condition 2 discussed in previous section, the Eg orbital set in octahedral geometry cannot generate any orbital magnetic moment. Hence, the dx square y square and dz square orbitals means Eg orbital set are known as non-magnetic doublet. These orbitals are non-magnetic in the sense of orbital magnetic moment. However, spin magnetic moment is still generated by these orbitals. Orbital contribution from T2g orbital set. The T2g set of orbitals means dxy, dxz and dyz are similar in energy, shape and symmetry. For example, the dxy and dyz orbitals are degenerate. Moreover, the dxy orbital can be transformed into dyz orbital by rotating it through 90-degree about the z-axis. There is a further factor that needs to be taken into consideration. If all the T2g orbitals are singly occupied, an electron in say dxy orbital cannot be transferred into dyz orbital because it already contains an electron having the same spin quantum number as the incoming electron. If all the T2g set orbitals are doubly occupied, the transfer is not possible. Thus, only configuration which have T2g electron other than 3 or 6 electrons make orbital contribution to the magnetic moments for octahedral complexes. Thus, octahedral complexes with D1 and D2 configuration will have orbital magnetic moment, but the octahedral complexes with D3 configuration will not. The expected orbital contribution in high spin octahedral or tetrahedral complex with any of the D1 to D10 complexes is shown here in the table number 4. This table also lists the ground state terms corresponding to the Dn configurations when an electron distribution can take up only one arrangement. The corresponding ground state term is singlet A. When two arrangements are possible, ground state term is doublet means E. For three arrangements, ground state term is triplet T. In a term symbol, the left hand superscript denotes the spin multiplicity and the right hand subscript G indicates Girard. Looking at the table, it is clear that metal ions having A and E ground state terms do not show orbital contributions. However, those having T ground state terms are expected to show orbital contributions to the effective magnetic moment. This explains why the effective magnetic moment for tetrahedral nickel 2 plus, octahedral cobalt 2 plus, and octahedral Fe 2 plus complexes is higher than the spin only value. An example helps us to understand the quenching of orbital movement in different metal complexes. Let us consider nickel 2 plus means D8 complex as a free ion. The total magnetic moment mu L plus S is calculated to be 4.47. In octahedral D8 complex, the orbital contribution is 0. On the contrary, D8 tetrahedral complex will have contributions from the orbital magnetic moment. Hence, although both the complexes have two unpaired electrons, the hexaaqua nickel 2 plus complex has magnetic moment close to the spin only value, but the magnetic moment of tetrachloronickel complex is higher than the spin only value. Orbital contribution from excited states. From above discussion, the octahedral nickel 2 plus and tetrahedral cobalt 2 plus are expected to have no orbital magnetic moment, but only spin magnetic moment. However, such a complex in reality exhibits a magnetic moment significantly higher than mu s. This is because the excited states of octahedral nickel 2 plus and tetrahedral cobalt 2 plus carry the orbital magnetic moment. In a system having such an excited state, the spin orbit coupling brings about some mixing of ground state with the excited state, thus forcing some orbital contribution. The quantitative relation between mu effective and mu s is mu effective is equals to mu s into 1 minus alpha lambda upon delta plus 2 alpha n beta square upon delta, where alpha is a constant which depends upon the ground state and the number of d electrons. The value of alpha is 2 for Eg ground state term and 4 for an A2G. Delta is the separation between ground and the excited state and can be obtained from the electronic spectra. Lambda is the spin orbit coupling constant and it is positive for D1, D2, D3 and D4 ions and negative for D6, D7, D8 and D9 ions. The first term alpha beta square upon delta arises from the mixing in of an excited state via spin orbit coupling, and the second term 2 alpha and beta square upon delta is the temperature independent paramagnetism, which is a field induced. Now it is clear from the above relation that the greater the 10 dq value, the smaller the mixing effect. Therefore, the lesser orbital contribution. It explains a strong donor ligand is likely to reduce the orbital contribution. Further, depending upon the sign of lambda, mu effective will be higher or lower than mu s. For example, the sign of lambda is negative for nickel 2 plus and positive for chromium 3 plus ion. The high spin octahedral complex of manganese 2 plus hexaaqua manganese 2 plus with the ground state 6a1g has no excited state of same spin multiplicity as that of the ground state. Therefore, mixing of the ground state with any of the excited states due to spin orbit coupling is not possible. Thus, there is no orbital contribution to mu effective due to spin orbit coupling. Therefore, mu effective is same as mu s. In high spin octahedral complexes of cobalt 2 plus, the ground state is 4t 1g and a large orbital contribution to the magnetic moment is expected. Mixing of excited state lowers the magnetic moment somewhat, but a value of mu effective is still larger than mu s in excess of 5 Bohr magneton is usually found. The ground state for the tetrahedral complexes of cobalt 2 plus is 4a2 and a low magnetic moment approaching to spin only value might be expected. However, an excited magnetic state is comparatively low in energy in the tetrahedral complexes and can be mixed with the ground state. So the magnetic moments in the range from 4 to 5 Bohr magneton have been predicted and are found experimentally. An inverse relationship exists for tetrahedral complexes between the magnitude of the magnetic moment of the complex and the value of delta as predicted by the equation number 5. In general, using three conditions discussed in previous section, it is also possible to make out whether a low spin octahedral configuration will have orbital contribution or not. For example, in a low spin complex of manganese 2 plus, the ground state is 2T 2G and therefore fulfills all the three conditions. So the complex will have orbital contribution. The ground state for low spin complex of iron 2 plus ion is A1G, but all the electrons are paired and hence the complex is diamagnetic. Moreover, the ground state for low spin complex of cobalt 2 plus ion is 2Eg and hence it has no orbital contribution. For the 4D and 5D ions, diamagnetism results for even number electrons and paramagnetism to the extent of one unpaired electron only is observed for the odd numbered electrons, indicating that spin pairing takes place for these ions as far as possible. This may be due to reduced interelectronic repulsions in large-sized ion, reducing the electron pairing energy, and second, higher ligand field splitting. The mu at room temperature is generally lower than mu s and cannot be used to determine the unpaired electrons due to third, high spin orbit coupling constant, which align L and S vectors in opposite directions, destroying the paramagnetism. Further, 4. The Curie or Curie-West law does not hold. The variation of mu with L is complex and depends upon the number of electrons present. Some ions like MnO4 negative, CrO4 2 negative and low spin cobalt 3 plus complexes show temperature independent paramagnetism even though they do not have any unpaired electron. This is due to the spin orbit coupling of the ground state to a paramagnetic excited state under the influence of the magnetic field. The degree of mixing is independent of temperature but depends on the applied magnetic field, as the excited state is well separated from the ground state whose population does not change with temperature. Quenching of orbital magnetic moment due to loss of orbital degeneracy. The loss of degeneracy of 5d orbitals affects the unrestricted motion of electrons about the nucleus. The degeneracy of d orbitals is lost to a greater extent in case of tetragonally distorted octahedral complex, trigonal bipyramidal complex and square pyramidal complex. In such a complex, the magnetic moment mu effective is close to mu s.
Summary. In this module, we discussed that the magnetic moment of the most of the transition metal ions are very close to spin only magnetic moment mu s, means completely neglecting the orbital motions. The magnetic behavior of the coordination complexes can be easily explained based on the crystal field theory. Strong field ligands having very high splitting energy lead to the formation of the low spin complexes. However, weak field ligands having low splitting energy lead to the formation of high spin complexes. In some transition metal ions, spin orbit coupling takes place and contributes to the overall movement. For spin orbit coupling to occur, following three conditions must be satisfied. There must be a half-filled or empty orbital similar in energy. Second, there must be a half-filled or empty orbital similar in shape and symmetry. Third, the nearby symmetry related orbital must not contain an electron with the same spin as the first electron. The loss of degeneracy of the d orbitals affects the unrestricted motion of electrons about the nucleus. The degeneracy of the d orbitals is lost to a greater extent. In such a complex, the magnetic moment mu effective is close to mu spin.